Good morning. Today we are going to discuss functional dependencies. Functional dependency in the sense, uh, if you are going to design a table, a number of dependencies exist among attributes, and the definition of functional dependency is like this. Functional dependencies are used to specify formal measures of the goodness of relational designs, and keys are used to define normal forms for relations, and functional dependencies are constraints that are derived from the meaning and interrelationships of the data attributes. A set of attributes X functionally determines a set of attributes Y if the value of X determines a unique value for Y. For example, I will show you functional dependency. Functional dependency determines the relation of one attribute to another attribute in a database management system or table. Functional dependency helps you to maintain the quality of the data in the database. A functional dependency is denoted by an arrow. The functional dependency of X on Y is represented as X determines Y. Functional dependency plays a vital role to find the difference between good and bad database design. For example, here we have a table. Here employee number, employee name, salary and city. Here employee name is the primary key here. So we can say that employee name is dependent on employee number, salary also dependent on employee number, city also dependent on employee number. Why? There can be many employees with the same name. Salaries of many employees may be same, and there are many employees working on the same city. But employee number is unique. Once you know the employee number, you can determine his name, salary as well as city. So here we can say that employee number determines employee name, employee number determines salary, and employee name determines city. That means here that is about functional dependency. That means employee name is dependent on employee number, salary also dependent on employee number, and city also dependent on employee number. Okay, that is functional dependency. And next is functional dependency X determines Y holds whenever two tuples have the same value of X, then they must have the same value of Y. For example, suppose that X is the employee number and Y is the employee name. Then if for every X there is a unique Y, for every X there is a unique Y means if you take X, that means T1 of X is equal to T2 of X means, suppose that in a tuple T1 of X, that means T1 of X means if the attribute X is the attribute X of T1 and attribute X of T2 are same, then definitely Y should also be the same. Now X determines Y in R specifies a constraint on all relation instance R of R. Written as X determines Y can be displayed graphically on a relation schema as shown in figure. Functional dependencies are derived from real world constraints on the attributes. Okay. Now examples of functional dependency constraints. Social security number determines employee name, right? That means social security number is unique, but once you know the social security number, you can easily access his employee name. Project number determines project name and location. That means project number is unique and project number determines project name, project number determines the location in which that project is going on. Employee SSN and project number together determines the hours per week that the employee works on the project. That means SSN and P number. SSN uniquely cannot determine the number of hours. That means once you have a project number and the social security number of the employee, that means this employee is working on this project for this many hours. That means this SSN and P number together, that's a composite key, that together determines hours. An FD is a property of the attributes in the schema R. The constraint must hold on every relation instance of R, and if K is a key of R, K functionally determines all attributes in R. Okay. Now, inference rules. Before going to the details of these inference rules, I am willing to go through another one here. These are the rules of dependencies. These are the types of functional dependencies: multi-value dependency, trivial functional dependency, non-trivial functional dependency, and transitive dependency. Multi-value dependency means multi-value dependency occurs in the situation where there are multiple independent multi-valued attributes in a table. Multi-valued dependency is a complete constraint between two sets of attributes in a relation. For example, here this is the car model and this is the manufacturing year and this is the color. Okay. In this example, manufacturing year and color are dependent on each other but dependent on car model. Okay. Dependent on car. In this example, these two columns are said to be multi-value dependent on car model. But our focus is not on multi-value dependency. We are focusing on trivial functional dependency. Trivial functional dependency is a set of attributes which are called trivial if the set of attributes are included in that attribute. For example, employee ID determines employee ID. That means employee ID determines employee ID. That is a trivial functional dependency. Employee name, employee ID and employee name together determines employee ID, because that right hand side is a subset of the left hand side, so that is also trivial. Employee ID, employee name together determines employee name. That means right hand side is a subset of left hand side, then that is called trivial functional dependency. Okay. Now, non-trivial functional dependency means functional dependency which also known as non-trivial dependency occurs when A determines B holds true where B is not a subset of A. For example, here this is the company name, this is the CEO name, and this is the age of that CEO. Okay. Now, company determines CEO means once you know the company, you can easily find out CEO. But CEO is not a subset of company. CEO is not a subset of company. So, that is non-trivial functional dependency. Then we are going on to transitive dependency means transitive is a type of functional dependency which happens when T is indirectly formed by two functional dependencies. For example, company determines CEO and we have a list of CEOs and CEO determines age. That means the age of Satya Nadella depends on him, not on the company. Okay. And age of Sundar Pichai is depend on Sundar Pichai and not on Google. Okay. So, company determines CEO and CEO determines age. Therefore, according to the rule of transitive dependency, company determines A. That means A determines B and B determines C, then definitely A determines C. That is called transitive dependency. And we are coming back to our PPT. Here, given a set of, these are the inference rules for functional dependencies. Given a set of functional dependencies F, we can infer additional functional dependencies that hold whenever FDs in F hold. Reflexive rule means if y is a subset of x, then x determines y. If y is that is trivial functional dependency. If y is a subset of x, then definitely x determines y. That is reflexivity. That means every determinant determines itself. That means x determines x and y determines y. If y is a subset of x, then also x determines y. That is reflexivity rule. Then augmentation rule is if x determines y, then xz determines yz. If x determines z, xz determines yz. Then transitivity, as I told you earlier, if x determines y and y determines z, then x determines z. These are inference rules 1, 2 and 3. These are very important: reflexive rule, augmentation rule and transitivity rule. These rules hold, and all other rules that hold can be deduced from these. Next is decomposition rule. If you have x determines y z, you can split that into x determines y and x determines z. Okay, that means if social security number determines employee name and social security number determines so the project in which he is working, then you can definitely split that into SSN and name, SSN and project number. Okay, now union. If you have two relationships or two functional dependencies, x determines y and x determines z, you can combine those two as x determines yz. Then pseudo transitivity. If x determines y and yz determines z, if x determines y and if x determines y and wy determines z, then wx determines z. The proof is not required. The last three inference rules as well as any other inference rules can be reduced from a reflexive rule, transitive rule and earlier rules. Reflexive, augmentation and transitive rules. Next is now inference rules for FDs. We are continuing. Closure of a set of functional dependencies is defined as F plus. You are given a set of functional dependencies, and the closure of that set of functional dependencies F plus is all FDs that can be inferred from F. F is a set of functional dependencies, and closure of F means that is all functional dependencies that can be inferred from F. Closure of a set of attributes X with respect to a set of functional dependencies F is the set X plus of all attributes that are functionally determined by X. X plus can be calculated by repeatedly applying IR1, IR2 and IR3 using the FDs in F. Okay. Equivalence of set of functional dependencies. So here I am going to show you how to find the closure of a set of functional dependencies. Now we are going to find out closure of X under F. That means F is a set of functional dependencies. Here this is an example. Here the functional dependencies are AB determines C, A determines DE, B determines F, F determines GH and D determines IJ. These are the functional dependencies for this relationship. This is a table, and that table is having this much number of attributes: A, B, C, D, E, F, G, H, I, J. Okay, that means 2, 4, plus 4. That means 10 attributes are there. Among that attributes, we have the functional dependencies. A B determines C, A determines DE, B determines F, F determines GH, and D determines IJ. That means, suppose that closure means closure of A. Closure of A, that means that is represented by A closure, is the set of all attributes that can be reached from A. Using A, what are the attributes that you can reach? For example, here, trivially, I am going to have A plus. A plus include A. That means from A you can reach A, no problem. Okay, you have to write A here. Now, see, now this is the A closure till now. A closure is this, and now search for the functional dependency where the left hand side of that is a subset of this A plus. Left hand side should be a subset. Left hand side of this functional dependency should be a subset of this. Here we are having only A, and subset of A is the largest subset is A itself. So look for A on the left hand side. Here A B determines C. So A and B should be there. We don't have A and B here. Here A determines DE. That means this is a proper subset of, this is a subset of this A closure. Then you can include the right hand side in this. That means D and E can be added here. That means, okay, D and E are added. Then we are searching. That means B is not here, F is not here, D is there. Okay, D is already there. Then you have to include the right hand side, I and J here. Then coming back, again you are scanning from. That means this process has to be repeated until there is no possibility for the expansion of A plus. Now, AB is not a subset of this. A is a subset of this. We have included D. What about B? B is not a subset of this. F also is not a subset of this. D is a subset of this. So we have already added this. That means here A plus is, or the closure of A is A, D, E, I and J. These are the attributes that can be reached from A plus. So if this has to be a primary key, all attributes has to be reached from this A. If A has to be the primary key. Now I am going to check whether AB plus. Now I am going to have AB plus. That means the closure of A and B together. Definitely AB closure include A, B. That means that is trivial. AB closure includes A and B, that is trivial. Now search for the left hand side, which is a subset of this. That means here AB is a subset of AB, so you have to include C. Okay. Now what about here? For this functional dependency, left hand side is A, and that is also a subset of this. Then you have to include D and E. D, E. Then next one is B. B is a subset of this. Then you can add F. Then what about F? GH. F is present here, so you have to include GH. GH. And now what about D? D is a subset of this. This is I, J. That means every attribute is included here. Every attribute of this is included in AB plus. So this AB can be chosen as a primary key. That is closure of AB plus. So closure of, what about closure of G? Closure of G, for example. Definitely closure of G includes G. That is trivial. trivial functional dependency, that is G determines G, that is trivial. So G plus include G, and you are looking for the left hand side which is having a subset of this. See, left hand side is not having any pair G. G is not there on the left hand side anywhere. So G plus is only G. From G you can reach only G. Okay. What about BC plus? BC plus means closure of BC. What about closure of BC? So trivial one BC. Now look for the left hand side which is a subset of this. Here AB, A. What about B? B is a subset of BC, so you have to include this F. Then what about F? F is a subset here. F determines GH, then we are going to include G and H. Again, coming back to the starting point, what about AB? AB is not a subset of this. A is a subset, not a subset of this. B is a subset of this. F already included. F is a subset. G and H already included. D is not a subset. So here, if you take B and C together, if you find the closure, then we have only this much number of attributes. This is the way we are going to find out the closure of a set of attributes under a set of functional dependencies. Closure of a set of attributes under a set of functional dependencies. So in a table, for some set of attributes, if the closure includes all attributes, then that can be chosen as a primary key. Here, AB can be chosen as a primary key. Why? Here, this relationship is having this much number of attributes, and all those attributes are there in AB plus. That means closure. That means every attribute of this relationship can be reached if the value of A and B are available. Okay. Now we are going through the algorithm for this. Input is closure of X under F. X means this is a set of attributes, set of one or more attributes. You are going to find out the closure. Here X is A, here X is AB, here X is G, and here X is BC. And the set of functional dependencies is this set of functional dependencies. F the set of functional dependencies are the set of attributes. F the set of functional dependencies. This is F. F the set of functional dependencies and R the set of attributes. This is the table and these are the set of attributes, and X is a subset of R. X is a subset of R means here this should be a subset of this. This is a subset of this. This is a subset of this. That is the condition. And here the algorithm works is this is trivial functional dependency. X plus includes X. That means functional dependency. That means here your functional dependency here the closure includes that itself. Then repeat old X plus. That means finally this old X plus contains is equal to X plus. That means that is assigned to X. For example, I will show you what will happen if you proceed with this one. Okay. If you proceed with that one, then I will show you what will happen. See, now X plus means here I am going to find out A plus. Initially, A plus include A. A plus include A. That is trivial functional dependency. Repeat old X plus equal to X plus. Now we are going to have old A plus equal to A. Now old A plus equal to A. Then for each functional dependency, Y determines Z in F. Do. That means we are going through this and for each functional dependency, here how many functional dependencies are there? 1, 2, 3, 4 and 5. For all these 5 functional dependencies, if x plus, if this is a subset of, if this is a superset of y, that means if you have a functional dependency yz, and if this y is already there in x plus, if this y is already there in x plus, then you have to include x plus subset equal to x plus union z until old x plus is equal to x plus. That means here you are going to include, now a plus is having a plus is having a, and you look for the left hand side of each expression. This is y determines z. If y is there in x plus, that means if a is there in a plus, then look for the left hand side. Here for this functional dependency, a determines de, a determines de, then this a is a member of a plus, so you have to include the right hand side, a d e. So you have included d and e here. Okay, d and e here. That means if x plus, if a plus is a superset of y, then we have included this is a, that means right hand side to this until old x plus is equal to x plus. That means old a plus and a plus are different here. Now coming back to here, then we are copying this a d e here. Okay. Now again for each function dependency y z, that means a d e. Here a b not there. A we have already included d and e. What about b? It is not here. What about f? F is not here, but D is there. Now you have added I and J. You have added, and now here coming here, old x plus and x plus are, old a plus and a plus are different. Then coming back to this point, then old x plus is equal to x plus. That means you are copying this to this place. Then I, J. Then for each FD, y determines z in F2. That means here for all these functional dependencies, you are going to AB is not here, A is here, already included D, B determines F, not present here, F determines GH, F is not here, D determines IH, D is here, so I and J already added. That means no change, no change. Now if you reach this place, now this old a plus and new a plus are, old a plus and a plus are same, then you can continue. That means this is the closure of A. So this is how the algorithm works. Okay, so that's all about functional dependency and how to find closure of functional dependencies. In the next session we will discuss how do you find out the minimal cover as well as cover of a set of functional dependencies. Okay, thank you.